Last time we did this ANOVA, we did not use a real data set. There was an easy one that said, use this for ANOVA, so we used that. We did the ANOVA, and I showed two functions. One is AOV. The other, ANOVA, applied to something called LM. And what does LM stand for? Linear model. So the next topic, I've decided to use linear model because that's quite important in statistics. Linear model, general linear model, you will see that they are closely related. We looked at the p-value, which was 0.2121 last time, and that concluded that there are no differences in the means between the two groups, and that's where we left off. Good. Now we have to, let's pick a real data set. So this is original data from Ronald Fisher. I don't know if you know what his name is. Way back when he came up with Fisher's test, settle down, Flippy, correlation, etc. So the data itself there it is. We have, ready? We have sepal length, sepal width, petal length, petal width. We are talking about an iris flower. Yes?
Not I biology department. What is a stem? Is this a stem? Yeah. Okay.
And petal, you know, petal.
Petals, I know what the petals are, but I was just making sure.
And there are three different species. One is Setosa, the other versicolor, and the last one Virginica. So we have three different species, and Fisher wanted to know all. I don't know why, but he picked this data set to see differences. Can we use an ANOVA to compare the averages of the three species, averages of blank for the three species? Should we pick sepal length, sepal width, petal length, petal width? Whatever is not an option.
Whichever was normally.
Whichever is not an option. Pick one. Petal length. I'm going to go with petal length.
So you could have done whichever one you wanted to do.
I waited, but you all disappointed me.
Wow.
So A, going to subset on the species Setosa and graph petal length. Peter. Come again. Why is it what?
Why is it outside of parentheses?
I can keep it inside. but I wouldn't be able to subset with respect to species. The next one, I'll go for versicolor, and the last one, Virginica. So they're all petal lengths, and again, if you search machine learning or whatever, you will see this data set, but they won't just use petal length. They would use width, length, all of those. I'm going to create a data frame. People who took my contact class probably remember this. You don't?
No, I remember.
You didn't even take it.
Got you there.
So all I'm trying to do is subset and create a new data frame. There is a reason why I'm doing it this way.
That's so cute.
Box plot of Wednesday. Wednesday.
Sandy, I like those better than box one.
Can we put purple as one of the colors?
Sure.
It's like a purple flower.
So I'm going to plot the density of petal length for Setosa first. Hopefully they are different. Petal length not done. What? Hmm. Five variables. Petal.
It does. It's like, oh, I'm looking at it, I was like, nice.
Okay, so that is for the first species, which is Setosa. Purple. Do we agree that it is normal? Yes?
Yeah. I would say so.
We have some bumps here and there, but they happen because of density estimation. The next one, I'm going to plot the versicolor species. Fingers crossed. Hopefully it's different.
Thank you.
I do like that color thing.
Yeah, I like it. Why is it blue?
Baby.
Why is it
I don't like her.
blue?
Yeah.
Is it inside?
Interesting.
Okay. Should be outside of density. So I have the first one, but the second one isn't getting added, the pink one. So I'm going to do add equals true. Let's try it outside. We can add later. So the previous one, the center was at 1.4. This one is slightly over. It's at 4.0. What is the next one? Last?
Probably not.
Probably not. What do you mean?
I was like reading the whole. So,
If I'm going to use another color, forest green.
wait, that's not the vibe though. Oh, it is the vibe, you're right. You're right.
19 warnings.
I was actually gonna suggest teal, but isn't that like brighter?
And that is the last one. Would we consider this to be normal? It doesn't look like it, but we will see. As of now, we're doing subjective stuff. That looks normal, that looks normal. The last one may be normal. So what is an objective way to come to a conclusion? Oh, good. Catch. No,
Okay, so maybe it is normal. Oh.
but it'll be different.
Yeah, I
So
know. I saw now.
just by observing, do we think that there are differences between the three species? Yes, no, maybe?
Yeah.
Yes, there are differences, possibly. For some reason, it is not adding today, and it's bothering me. I know why. It is adding, but we're just not able to see it. I'm going to go from 0 all the way up to 8. So one is over here in the range of 1.4, the others are far away. So, and That's such as the data that we get. From the looks of it, do we believe that the average petal length for the three species are different? Yes. The purple one is Setosa. The pink one is versicolor, and the green one is virginica. So Setosa is the primary cause of difference. Do we agree?
Yeah.
Versicolor and virginica, they seem close, but could I just say that they are the same? Pack our bags and leave? No, we have to do the tests later. Do you think that ANOVA will reject the null?
Yeah,
Why, Omar?
there's at least one different.
Why?
There's at least one different.
Okay. Go. Are there differences in average petal length based on species? What is the ANOVA null? No difference in the mean. So mu for Setosa is equal to mu for versicolor, which is equal to mu for virginica. What is the alternative? At least one of the means are different. Don't put that they are not the same. That is the incorrect. No. At least one of the means are different. So we can use, either use AOV or ANOVA. I'm going to go with AOV, but prior to that, I'm pretty sure that the data is going to satisfy normality. So let's validate assumptions first. Assumptions. The first one is normality. Just by looking at the pictures, I think they are. But how do we do it properly? Okay, Shapiro-Wilk. The first one is for Setosa. The second one is for versicolor. And the last one is for virginica. But let's go ahead and run, see what happens. Incorrectly? Yeah. Okay. Setosa result, I get 0.05481, slightly over 0.05. Seems like a borderline case. Let's just assume it's normal. Still it's over 0.05. But in practice, I will say that we need further investigation. What about versicolor? Normal? Not normal? It is normal because p-value is greater than 0.25. We don't reject the null. The last one, what do we think? normal. So this one, borderline 0.05481, but we can conclude that they are normal. Just for the sake of this example. What is the next assumption?
Variability.
Okay, so how do we verify variability? What did we use last time? Levine. Very good. The first assumption is normality. Second, we'd like to have identical variances. Do we think that they have identical variances?
No,
No. Why not?
these are not very far apart.
The last two maybe, but the first one definitely not.
Aaron says the last two, maybe. The first one, definitely not. How did you identify that, Aaron?
The first one is so scrunched together, the data, that it's not as spread out as the other two.
Very good. So this one seems squished, and those two, the spread seems to be sort of similar. Now, something that we want to make sure is that all three samples are on the same picture. If they're not on the same picture, you may not be able to say if the variances are different or the same. Looks like the same in all three cases, right? So when you're doing comparisons, they have to be in the same picture. So living test and do it directly for species.
It's easy to see if they're all the same picture, but if you want to look at the axes, you probably need the information to figure it out.
Can't hear you, Nikki.
You were talking about how they all have to be in the same picture, but if you looked at the axes and the individual pictures, you might be able to figure out.
You can, but it's just not
It's
good.
definitely easier.
Right, and especially if you are, delivering this information to someone else, they may not be as astute as you are, and they might think, oh, they all have the same variances. So it's just a better way of delivering.
Quick question.
Yes.
So you look at like how the data is spread in
Mhm.
each curve, or you look how far apart each of the curves are for variation, or both?
Okay. Would someone like to answer Phoebe's question? So Phoebe's question is, well, should we look at how spread they are or how far apart they are? How spread they are. Far apart, testing to see how far apart the averages are. The center is here, center, center. That is the job of ANOVA. ANOVA is going to tell us if the averages are far apart or not. So let's go ahead and run and see what happens. Species not found. Forgot to do this. Most other packages, the data set simply called iris. Even in Python library. Okay, so that is our Levine's test output. Levine's test is the test for homogeneity of variance. And we can change the center. But We can use the mean instead. The result is not going to change. Perhaps they used it because median is a better estimator for the center than the mean. So, didn't change anything. Based on what you see, do you believe that the variances are equal?
No.
Why not, Vicky?
I was just looking at the probability,
Mm-hmm.
and it's like a lot smaller than a 0.05.
It is the p-value, the probability that we see is extremely small. So it is violated. P-value extremely small when compared to 0.25. Double less than would simply mean extremely small. Standard notation. Yeah, you could do triple if you want, but double is standard. But for the sake of the example,
We're ignoring it?
yep, just for the sake of illustration, let's assume that assumptions hold true. I'll just put let's proceed.
Let's just keep going.
Let's just keep going. In practice, you can't do this. FYI.
I won't tell anyone more.
Okay. If you remember. Okay, so what do we use? We can either use the ANOVA argument or the AOV. In this case, I'll just go ahead and use AOV. Want to compare the petal lengths and regressed on species. The data would be irises. Good. Okay, and that's what I get. I see the sum of squares, degrees of freedom, but I don't see the full ANOVA. You can do summary of iris dot ANA, and that is the ANOVA summary. Based on the summary, do you think that we should reject the null? Easy question.
Yeah.
You should not reject the null?
It's like extremely
No,
small.
yeah.
Yes, we're done. We're done.
Why?
Final answer.
Why?
Because the probability is like really small.
Okay. So the p-value that we see, extremely small, it's like close to zero. Not only that, in general, a large F value, thousands or even hundreds would indicate that you are going to reject a null. It's an easy way, but of course, F and the probability are related, but standard process to recognize, oh, F is pretty large, we should probably reject the null. So based on the results that we see, our conclusion that there are significant differences among the three species in averages. In average petal length among three species. However, we've got to be careful the assumptions are in fact violated. Good. Okay. No, come again. Right there? Oh, this one? So it is extremely small. The p-value is extremely small. We reject the null. And since we reject the null, the average petal length, they are different. We will reject, we can conclude there is evidence to support that there are significant differences in the average petal length at a level of 0.05. Now that we know that there are differences, one might wonder, well, which two are different? Yes? But prior to getting into that part, I am going to show you a non-parametric equivalent of ANOVA. We're not going to get into the theory of it because it's a bit difficult. Very good, yes. Do we remember Paul, Leo? Starts with K. Cruscal Wallace. Think of Key West. KW.
Oh, I thought you said name of the,
In R, you can do Cruscal dot test. Same format can be used, but as I said, since R is open source, sometimes consistency is not there. Okay, so I'm going to go ahead and print iris.kw. This is for later reference. I forgot to put it in the code. Okay, let's see. Source. If you look at Cruscal Wallace, the p-value is 2.2 times 10 raised to negative 16. So what is our conclusion?
0.
Huh?
Still-
0. What'd you say?
0.
0 what? Oh, you are rounding that p-value? That's not the conclusion I want, Jonathan.
0.
0.
I like that answer.
What is
Not
it?
wrong.
So Crustal-Wallace is doing the same thing, but is it using mean or median?
Yeah.
Median. But in general, they'd simply say location parameter is different. So Crustal-Wallace is giving the exact same conclusion, but in practice, based on what we see, which is reliable, but which one is appropriate, ANOVA or Crustal-Wallace? Crustal-Wallace is appropriate. The reason being it is non-parametric and it doesn't have assumptions on distribution. It is not picky about variability because median doesn't affect variability. Variances. Good so far. Now, which two paths are different? We already are in agreement just by looking at the pictures from earlier. The first one in purple is Setosa. The pink one is versicolor. The green one, Virginica. Setosa is going to be different from the other two. It's obvious. Well, is Virginica and versicolor also different in terms of finding averages? There are a couple of ways you can do this. So you can use the contrast option in R. I'm not going to get into that because we have to program it in a specific way. I have to get into what a contrast is. So a post hoc comparison can simply use a t-test in R, which will give us intervals. And why do we call it post? After what?
Our test,
What test?
our ANOVA.
ANOVA. It is done after ANOVA, post ANOVA, and you only do this if you determine that there are differences.
Yeah.
If there is no significant difference among the averages, it would be silly to do this. So first pair, I can compare the TOSA to versicolor.
I have a question.
Yes.
Since we use the Crustal-Wallace in our conclusion, would we still say that there's a difference in average petal length or just like
Median. Median location parameter. Good question. I'll put that here. Comparing medians. Sometimes we just call them location parameters and not go any further. So first pair would be Setosa. Versicolor. Now do you see why I created that data frame at the very beginning? Here's a question. What should we use? Should we use variances equal or unequal? Unequal. What?
I thought I was wrong.
She didn't have faith in herself.
We know that the variances from the data, the spread, they are different. Those two have unequal variances. The purple and the green one, unequal variances. The pink and the green one, equal, but I can simply do the unequal case
'Cause we're
regardless.
not sure. Right?
We are sure about these two. We have evidence to support that the variances are equal for the last two. Why not just do unequal? What is the name of the t-test when we have?
Welch's.
Very good.
Thank you.
The cursor. Oh, there it is. Not the mouse. And if you want to get really technical, it is a touchpad.
The touchpad.
I'm going to compare Setosa to Virginica. Let's see if we remember from a long time ago, there is a formula to determine the number of paths. Yes, do we remember that formula? From Wilcoxon,
Oh.
number of
Oh,
paths?
the pool of the variance.
No, the number of paths. N times n minus 1 divided by 2.
The 4 was to find the,
Go ahead.
wait. The
Find the weight.
expected value.
Very good.
Thanks, guys. Over here, over here.
You'll have so much fun and problems with that.
You don't have to do that.
And the last one is to compare, if you put it in the formula n times n minus 1 divided by 2, or k times k minus 1 divided by 2, you will get 3. K is the number of groups that we have, which is species in this case. And of course, we don't want to do this manually. There are ways to do this using R. You can Google if you are interested. I just don't want to complicate things. The last pair would compare Versicolor to Virginica. Ready? I should have used print. Edit, find.
Are we still gonna compare the
We are. I just got excited and did something else. Okay. So the 3 cases, the first one is comparing Setosa to Versicolor. The average difference is about 2. setosa is less than the average petal length for setosa is less than the average petal length for versicolor, about 2, and you can see 0 does not fall in that interval. Okay, the next one, setosa virginica, the average difference is from negative 4.25 to negative 3.92. So setosa is less than virginica. And the last case, versicolor and virginica, right over here, is that different? Are they different? They are different as well. So every single pair has different means. Average of setosa is different from average petal length of versicolor virginica, and these two, one in pink, one in forest green, versicolor and virginica averages are also different. Good. So every pair of means is different. And that is our conclusion. When you do this in R, you look at the results, and ANOVA says reject the null, Kruskal-Wallis says reject the null, and then you do the pairwise test, and they all say do not reject, no difference. It simply means you made a mistake, right? At least one of them has to be different.
So what if there's like 10 different groups and like how do you pair all those?
Contrast.
Okay.
Can I see the print again?
If we have too many groups to compare, there is no way I'm going to sit around and compare them manually. There are 45 pairs to compare. I would simply program it. As I said, I didn't want to complicate things. Are we clear?
Yeah.
Okay. So that is the practical example for ANOVA.